So, welcome to GeNoCAS. Our speaker today is Alistair, and the title of his talk, as you can see there, is Homology and K-theory for self-similar group actions. Please, Ali, go ahead.
All right, thank you very much for the introduction. Thanks for the invitation to talk about this topic. So yeah, this is a paper I wrote with Ben Steinberg, and yeah, it's quite fun to talk about, so I'll get into it. So the topic is these self-similar group actions, which are really these objects that come from group theory, dynamics, and really what they're famous for is being really great ways of building exotic groups while still doing it in quite a simple way. So the most famous self-similar group is the Grigorchuk group. This was the first group constructed to have intermediate growth, and therefore also the first group shown to be amenable but not elementary amenable. And what I'm going to be talking about is these constructions that Nekrashevych introduced of both a groupoid and a C-star algebra that you associate to this self-similar group system that you have. And the point here is that these sort of represent some kind of underlying non-commutative space that these dynamics sort of work with to represent these dynamics. And indeed, he has some nice results that tell you, under certain nice conditions, you at the some of the C-star algebraic information actually determines the self-similar group. But I won't talk about that particularly today. But the point is, we have these nice groupoids and nice C-star algebras, and indeed the groupoid is a model for the C-star algebra. What the goal is of this paper and of this talk is to compute the K-theory of the C-star algebra and the homology of the groupoid. So these are invariants that are going to tell us quite a bit about these C-star algebras, especially because the C-star algebras we get are often going to be Kirchberg algebras. The K-theory actually completely determines the C-star algebra. And we're going to see some similarity between the K-theory of the C-star algebra and the groupoid homology, but that is not necessarily going to be like a tight connection between these things. So lots of people have studied the connection between the homology of a groupoid and the K-theory of the C-star algebra of the groupoid. And there's this so-called HK conjecture linking these. And so we're going to see some examples today that sort of fit into this framework and some examples which don't fit into that framework that refute the HK sort of idea. Okay, yeah, and yeah, just for K-theory, we get K0 and K1. For groupoid homology, we get H0, H1, H2, etc. Okay, so this is our goal. All right, so a self-similar group action, because really, I mean, there's some terminology difficulty here. Often people will talk about a self-similar group, and what they mean is a group of automorphisms of a tree. So here I've got a group that I'm considering to act faithfully on this infinite regular tree like this. So I have some group element G, and I'm going to think of the tree as the space of words in an alphabet X, a finite alphabet X. And so if I have something on the first level, I'm going to call it a letter. So if I have a letter X, like so, you can see my mouse, right? Yeah, okay. This has to be sent to another letter, let's say G of X. And now, because this is a tree automorphism, the subtree at this letter has to get mapped to the subtree here. But because these are all just infinite regular trees, then this subtree just looks like the other subtree. They both look like the whole tree, right? So what this automorphism G does from this subtree to this one is really just an automorphism of the tree itself. this automorphism we'll call the section of G at X, and we will use this notation here. And algebraically, this is expressed by this relation over here. So it says if you act on any word that begins with X, first you act on X, and you move it to this new letter, and then you act on the rest of the word by this new automorphism. Okay? And the group is called self-similar if this automorphism always lands back inside the group. Okay, so this is basically what a self-similar group is. And what I want to point out is that this is determined one letter at a time. So what I mean by this, I mean, suppose I have some word, X, Y, Z, and I want to figure out what my group element G is going to do to this word. Well, first I act on the first letter, I get G of X. Then I push past X, I get the section of G at X. This is a new group element, right? So now this just acts on the rest of the word, and I repeat. And all I have to know is how the group acts on the alphabet, so on the letters, and what this section is for letters in my alphabet. So this section has the structure of a cocycle, a one cocycle, meaning, if you will, this if you prefer, this is just a groupoid homomorphism where you view this as a groupoid with the action of G on the alphabet. Okay. So the reason for doing this is because now I can tell you what a general, not necessarily faithful, self-similar group action is. And we just define it to be a pair consisting of an action of the group G on some finite set X, viewed as an alphabet, plus some one cocycle for this action. So this is, again, we can just do the same procedure and we get an action of the group on the tree. So that's sort of where the word action comes from in this definition. But really it's just this action on the finite set and the cocycle for that action. Okay. And we'll call it faithful if this induced action here is faithful. So if this map includes into the automorphism group of the tree. So the most basic example is sometimes called the odometer or the adding machine. And this is where I've got decimal digits, and I've got an action of the integers on the decimal digits just by adding 1 more 10. But it gets interesting at the cocycle, because what the cocycle is going to do is it's going to carry the 1. So my cocycle of the generator of Z at each digit is going to be 0, except at 9 when I'm going to carry the 1 and I'm going to get 1 back again. Here I'm using some notation here to try and distinguish the numbers that happen in Z from the digits that happen in Z mod 10. So you get this behavior like this. This describes the action on the tree. So for example, if I had my generator A, this is going to add 1 to this string of digits here. It's just going to add 1 to the first thing, and then it's going to stop. But if I have a bunch of 9s, it will turn them into 0s, and then it will carry the 1 here. It will add the 1 to the 3 there, and it turns into a 4 here. And this is going to preserve the length of words. So 99999 is just going to go to 0, 0, 0, 0, 0, rather than adding an extra 0 or something like that. So we get a nice faithful self-similar action of the integers like this. Okay. But you can sort of see that this is encoding addition with decimal expansions, if you like. Okay. Now, I can already tell you about the most famous example, the Grigorchuk group. And indeed, we'll go and we'll compute the various K-theory and homology groups for this example in this talk. So what's happening here is that I'm saying I've got a binary tree, and then I am going to generate a group with 4 elements, A, B, C, D, where A is going to swap the 2 letters in my alphabet, and B, C, and D are going to fix the alphabet. And it gets a bit more interesting here with the co-cycle. So what is this diagram here telling me? This is saying that if I push my generator A past any digit, it's going to become the identity. If I push B past A, it's going to become, if I push B past 0, it's going to become A. If I push C past 1, it's going to, if I push B past 1, it becomes C. Okay. And you see there's this 3-cycle behavior going on between B, C, and D. So B pushes past 1 to become C, which pushes past 1 to become D, which pushes past 1 to become B. And I haven't actually given you the co-cycle or the action on the entire group, right? But I want to convince you that I can actually generate a group here. Like, I want to convince you that each of these A, B, C, and D actually does define an automorphism of this tree, right? So the point is that this data is all you need to define the map itself, because you start off with any random generator, so C in my case, and any random word, like this. First you act on 1, C fixes 1, you push past 1 to become D, D also fixes 1, becomes B, B fixes 0, becomes A. Now A swaps the 1 to a 0, and it becomes the identity, which then doesn't do anything for the rest of the thing. So this is what this generator does to this word. And you can do this with any generator, with any word. Okay. So at this point, it's easy to check, a little bit tedious maybe, but you can check these facts here. The A, everything has order 2, all of the generators, and B, C, and D, moreover, commute with each other and form this copy of the Klein 4 group. So yeah, D is equal to BC, for example. And something more is true, that actually all of what I've just said, so we get this faithful self-similar action of this subgroup of the automorphism group. I mean, it's faithful by definition. But actually, this is defined for us a self-similar action of this free product group here. With the same sort of arguments. And the quotient, so the faithful quotient of this free product group in the automorphism group, that's going to be the Grigorchuk group. This is not equal to the Grigorchuk group. This is not a faithful self-similar action. I mean, for example, we know this is not an amenable group, but we know the Grigorchuk group is amenable. But this is going to be crucial for us when we want to compute the homology of our groupoid that we build and the K-theory of the C-star algebra. Basically because this free product group here is so much easier to work with than the Grigorchuk group. Right. And it's not at all obvious at first why studying non-faithful self-similar actions can help us at all when we're interested in faithful ones, right? But the point is that often when you build this groupoid in this C-star algebra, which I'm going to leave as a black box for this talk. Just, if you've seen the construction of the groupoid and the C-star algebra before, then great. And if not, I'm not sure me going through that construction will help you much in this, online talk. But the point is, so if we denote this faithful quotient, the image of our non-faithful self-similar group within the automorphism group, if we denote this by G bar, then these are often going to get the same groupoid and the same C-star algebra. So this is an observation really by Nekrashevych for C-star algebras, and we've just lifted that observation to the level of the groupoids. And the point here is, don't worry too much about exactly what this says here. The point is just that there is some condition that's checkable, and in many nice examples this holds. But yeah, we're sort of saying that things that are in the kernel of this action of G acting on the tree, they're in there for a good reason. They're in there because at some point the sections of all words of length n become the identity. Bear in mind, if we're in the kernel, that by definition we're fixing all of the words, right? So this is going to tell us that this is telling us that we fix all the words for a good reason, because we fix all of the words up to length n. If we fix all of the words up to length n, and whenever we do that, we push past those words to become the identity, then we have to fix all of the longer words as well. And so therefore we're in the kernel. So this is these are the good elements of the kernel, and this is saying that all of the elements of the kernel are these good elements. Now there's a special class of self-similar groups, or self-similar group actions. They're called contracting self-similar groups. And I won't go too much into the definition of those, but it means that you have some finite subset n in your group, such that basically everything is attracted towards this finite set, in the sense that whenever you have any element in your group, then for sufficiently long words, it will push past that word to become an element of this nucleus. So then what that means is, in the above setting, we only have to check that each of the non-trivial elements of the nucleus acts non-trivially on the tree.
Sorry, what you said is not what is written there. So, for example, you said that n is finite, and then that if you start with any element and you apply the cocycle sufficiently many times, you get to n, but that is not there. Or how is that deduced from what is written?
So this is the definition of contracting.
Okay.
So I haven't shown the definition of contracting, yeah, I mean, I don't want us to worry about it too much, but this is a particularly nice...
Okay. Okay, I thought what was written there was the definition of contracting, but it's not.
Right, no, sorry. So what I'm saying here is that if you're contracting, so contracting self-similar groups are particularly nice self-similar groups, which are just presented by finitary data. And actually this finitary data here for the Grigorchuk group is an example of that. So this is going to be, both of these examples are going to be contracting self-similar group actions. And what this is saying is, so that you have that finite nucleus. In our case, the finite nucleus is going to be contained within these, like the identity identity A, B, C, and D. So it's at most the set of size at most 5. What this is saying is that you only have to check this condition now for the elements, the non-trivial elements, basically in this nucleus. So in our example just now, we know that each of the generators acts non-trivially, and therefore it satisfies this condition. So the point is, if we start off with the Grigorchuk group and we build our groupoid, we build our C-star algebra, or if we start off with this free product, G, which is the free product of C2 and the Klein 4 group, and we build our groupoid and our C-star algebra, these are going to be the same groupoid and the same C-star algebra. It's just now we're working with a much easier group. Okay. So now I can state the main theorem. And really this is our sort of theory. This is the general theorem that works for any self-similar group action that tells you gives you a long exact sequence for the homology and the K-theory. And then I'm going to go talk about how to apply it in this specific example of the Grigorchuk group. But in our paper, we really apply it to lots and lots of different examples. So the point is, this is really something that you can apply, and you can really compute these groups by using this theorem. I just want to show you this very special case of the Grigorchuk group as an example. So what does this say? It says that we have a long exact sequence where the groups we want to compute are 1 out of 3 terms, and 2 out of 3 terms are the homology of the group here. And moreover, we have a very explicit form for the connecting maps here between these things. I should note, I'm assuming here that the action of the group on the alphabet is transitive. This is only to make the statement look a bit nicer. Otherwise, we'd have to take a sum here over x from each orbit. But I mean, in any case, all of the nice examples that we want to look at have this property. It's really not too bad an assumption.
Another question. So is the group G the full group of the groupoid?
So the G is going to be right. So there's some subtlety here. So first of all, if G is faithful, so if this is a faithful self-similar action, then G is going to be contained in the full group. Really, what the full group is going to be is going to be a copy of V or a copy of Vn, where n is the size of the alphabet, and a copy of the faithful quotient here. So for any self-similar group action, it will be generated by this copy of V and this copy of G bar.
V being the Thomson group.
Yes, exactly. Thomson's group V. So, or Thomson's the related group Vn sitting inside the automorphism group of the n-ary tree.
And so what I was saying in that is where this sequence comes from. Is from a general sequence relating the full group, the homology of the full group and the homology of the group. Does it come from an open these exact sequences that you get when you get an open invariant open subspace or units or whatever it's called.
Yeah, exactly. So it's the latter, because really, I mean, I think the full group here in this situation of the groupoid is going to be too complicated to be that helpful. It's going to sort of, I guess the feeling is like it's, I mean, and sort of part of the point of this, right, is that the relationship between the homology of the groupoid and the homology of the full group is helpful. Like the mantra is that the groupoid has easier homology to compute than the full group has. So this is a way to compute the homology of the groupoid, which in turn, you can hope to use that to help you compute the homology of the group, the full group. But here, this is coming from exactly as you said. We build some big groupoid, and we find a nice closed invariant subspace of the unit space of that big groupoid, which we identify with this. So this is an example of a tight groupoid of an inverse semigroup. There's basically an inverse semigroup you can build, which is generated by G and X. And then this is going to be the tight groupoid, and the big groupoid is going to be the universal groupoid of that inverse semigroup. And then what's going to happen is, in this case, we get a very nice situation. It's sort of like a tuplet extension. So both the universal groupoid and the open invariant thing are going to homologically and K-theoretically look like the original group G. And that's how we get this exact sequence.
Okay.
And yeah, and we have the same in K-theory. These are really just the same exact sequence, just one's in K-theory, one's in homology. So yeah, I said that these are in terms of some, we can understand the connecting maps here in terms of some explicit maps here. So these two ingredients that I'm yet to tell you about are what's called the virtual endomorphism and the transfer map. Before I go into those, are there any more questions about this result?
One little question. So is there a map from the K-theory sequence to the group homology sequence?
Right. So I guess you would probably want to ask for the group to be torsion-free. And then you'd want to create... Are you asking for like a Chern character? Because then I guess...
Yeah.
I think there should be some sort of... I expect that some sort of Chern character should exist in this setup. I mean, certainly on the group level. I mean, there are some... Yeah, there should be a map the other way as well, at least. Well, okay, yeah. I mean, there should be... You sort of expect there to be spectral sequences at least, which approximate the K-theory with the homology, if you're in this torsion-free setting. There's some subtlety because these groupoids are often non-Hausdorff, and so we don't have those sorts of spectral sequences in that setting. But yeah. Another subtlety is that really this is about the full C-star algebras. These are all universal objects, these C-star algebras. So that might also sort of muddy some of the relationships. Although many of the examples we're looking at have a very amenable flavor, or at least K-amenable.
My questions originates because from the fact that with Guido, Arnone, and Del Gerasimov, we consider this in the totally algebraic setting. And in order to get the homology sequence and to get, I mean, we have a canonical map, the Dennis case, from K-theory to homology, but in order to make the diagram commute, so that one exact sequence maps to the other, we needed to impose strong conditions on the answer. So I wonder if you could get...
Yeah, interesting. I have to admit I've not thought too much about doing it in such a way that this all commutes, but one thing to note is that these maps are all sort of like, so I mean, because both of these things essentially come from this open invariant / closed invariant subset of the groupoid, right? Then as soon as you have your map from K-theory to, I presume, rationalized homology, that works nicely with respect to these open invariant inclusions, open invariant subsets of the unit space and the closed invariant subsets too, then you should get naturality like this. And so it'll be about sort of constructing functoriality of these. One way to do it would be to try and make these Chern characters, whatever that you construct, sort of functorial with respect to certain kinds of morphism of groupoids, like correspondences or these like partial actors, something like that. I would guess would be a way. But I mean, there's some stuff here because of the non-Hausdorffness as well.
Okay.
Cool. So yeah, I should also say this K-theory one, this is an instance of the 6-term sequence for a Kunz-Pimsner algebra, because we can realize these algebras as a specific kind of Kunz-Pimsner algebra. So yeah, this virtual endomorphism is quite easy to define. What it is if we consider the stabilizer of the action of G on the alphabet at some letter X, then this is going to be a finite index subgroup. And because it's the stabilizer, then the cocycle will actually just be a well-defined homomorphism from Gx to X. And it's called the virtual endomorphism because this is finite index in G, so it's virtually an endomorphism of G. So for example, this adding machine, the stabilizer at any point is just the multiples of 10. And the virtual endomorphism is going to be the divide by 10 map, roughly because we only carry the 1 every 10th digit. And a more interesting example is this Grigorchuk group example. And here I'm going to look at this free product G as the free product of the cyclic group of order 2 and the Klein 4 group. Now, this cyclic group of order 2 was A. This fixed the alphabet. This swaps the alphabet. So this is certainly not in my stabilizer of, say, the digit 0. But my Klein 4 group, each of these elements fix the alphabet. So Klein 4 fixes the alphabet. And in fact, it turns out the stabilizer is the normal closure of the Klein 4 group in this free product. And you can compute this virtual endomorphism directly on these generators. So on sort of typical elements of this normal closure, we can compute it like this, like below. And so we see, for example, here we're seeing this 3-cycle behavior from B to C to D. It's sort of appearing somehow in this virtual endomorphism, like this. Okay. So the other ingredient is the transfer map. And this works whenever you have a finite index subgroup. In our case, it's going to be the stabilizer. And I'll just sketch for you how this works in K-theory, but really we called this the transfer map because the analogous thing in homology is very well established and has been called the transfer map for like a century. Maybe this thing in K-theory must be known and called something somewhere, but it seemed sensible to call it the transfer map in this context. So suppose I have this finite index subgroup. It has a finite transversal T. So my whole group G just looks like the product of T and H. So I act by left multiplication on G. This gives me an action on the T-fold direct sum of C star of H. This gives me a star homomorphism into the T by T matrices, like this. So we have, this is the big group C star algebra, this is the small group C star algebra, and this gives me a map in K-theory, like this. And it doesn't depend on the transversal we picked, and this is what we call the transfer map. And so yeah, we have something analogous in group homology. So this is certainly very natural. And if we consider this basic example of the adding machine, then we have this finite index subgroup of multiples of 10. This also just looks like the integers as a group. So all of the K-theories and the first two homology groups are Z, and then all of the other homology groups are 0. So all of the groups that we care about are Z, and it's pretty easy to compute that all of these transfer maps are going to give us the times 10 map. So we have a transfer map for each index here. But yeah, it's pretty easy to see that each of these will be multiplying by 10. So altogether, this gives us, let's do the computation. Let's apply the theorem and compute the K-theory for the C-star algebra in this adding machine example. So we have this exact sequence from our theorem. And from what we just said, it boils down to this. So all of the K-theory groups that we know are Z. And the transfer map is the times 10 map on K-theory. The virtual endomorphism, we saw that was the divide by 10 map, which is an isomorphism. So in K-theory, this is just going to give us an isomorphism, i.e. the identity on Z. So altogether, this is the times minus 9 map. And from that, we just get that both the K-theory groups are Z mod 9. And in homology, we get basically the same thing. The same computation gives us exactly that the first two homology groups are Z mod 9, and everything else vanishes. So note that in this case, we do have an HK-like formula. Okay. So now let's do the Grigorchuk group example. So this C-star algebra that you get out of the Grigorchuk group, remember, part of the point of this was that the C-star algebra we get is the same whether we use the input data of the Grigorchuk group or whether we use the input data of the self-similar action of this free product here. So the point is that we get the thing we're interested in by considering this easier group here. And so now we consider this 6-time sequence like this. And thanks to Kuntz, we understand the K-theory of free product groups. It tells us that in K0, we get the direct sum of the K-theory of the group C-star algebras. And we mod out by saying that the unit coming from each group is identified in K0. So this gives us one copy of Z coming from the unit, plus one copy of Z coming from the rest of the cyclic group of order 2, because the C-star algebra is just two-dimensional commutative C-star algebra. And then we get 3 more copies of Z coming from K0 of this commutative 4-dimensional C-star algebra. And And in K1, you just get this direct sum, but now these are both finite dimensional, the K1 vanishes. So this is 0. So now we just have to compute what this map here does in K0. So we have z to the 5 on either side, and we just need to know the co-kernel and the kernel of this composition minus the identity, or the identity minus this composition. And we can compute what this map is. It turns out to be this very explicit thing. Where I have this 3x3 matrix here that's witnessing this 3 cycle I have that goes B to C to D to B. So as a result, you can just now do a basic computation that says K0 and K1 are both the integers. And moreover, the unit in K0 is going to be 0.
May I interrupt?
Yes.
So in your sequence, there was no groupoid. There were all groups. This is because the groupoid was replaced by this flip color group. Or...
So the groupoid is modeling the C-star algebra. I mean,
so all Greek is not the C-star algebra of gamma.
No.
Ah, okay.
Yeah. Sorry. So this is something I could probably have made clearer. So there is this C-star algebra. There's a groupoid in the C-star algebra that Nekrashevych constructed. But these are not this is not the C-star algebra of the group itself. It's another one that's built from this data. It's sort of like, essentially what you have is you have a graph algebra in there, or Kunz algebra really, coming from the finite alphabet. And then you also have a copy of the group C-star algebra, and it interacts. So you have a copy of the group and a copy of the graph thing,
like a
and they interact.
Mm-hmm.
Yeah.
Okay.
And so that's also sort of what's happening in this, like the topological full group has this copy of V, which is sort of like, it's a topological full group of the graph groupoid, right? And you have a copy of the self-similar group itself, and those interact. And so that's sort of analogous to...
And that's not the knowledge. I mean, you said it at the beginning, that the groupoid, the invariants of the groupoid were easier to compute than those of the group, and that were related by some exact sequence. And in this particular case, can you say something about the invariance of the group?
So as an invariant of gamma, I mean, I guess there's something slightly subtle here, which relates to so the groupoid here is an invariant of the self-similar action of gamma. So viewing gamma as a group of automorphisms of the binary tree. And so there's this difference between, so this notion of equivalence for self-similar groups, which is to do with this. And so equivalent self-similar groups are going to have, in particular, isomorphic groups, but like you forget structure when you just think about the group. So these things are not necessarily invariants of that group, I think. It'll be interesting to see what can be said. I mean, I think what we get is something about I think,
I think in the beginning you did write a sequence relating the two things. We didn't check it. That you wrote a sequence, you have a, like I think it was K-theory of the group, K-theory of the group, or maybe it was homology, and then that of the group.
This one.
Yeah.
Yeah, I mean, so the thing is that this is the natural exact sequence. And so now if I wanted to put gamma in here, like I also have, like in the Grigorchuk group case, right? I could also put gamma here and here.
Yeah.
Yeah,
because so the group is the same. Yeah.
Yeah, exactly. It's just that now the problem is that the group appears 2 out of 3 times, but the unknown appears 2 out of 3 times, and so you're a bit screwed.
Yeah. Understand.
I do think it's an interesting question, though, to see how much can be pinned down about the K-theory of the Grigorchuk group C-star algebra, or the homology of the Grigorchuk group, by sort of going a bit further, doing some more techniques. I'd be quite interested in that.
It's just one more silly question, and I need to go on. Is this the group, the Grigorchuk group, the one that every element is order 2?
I think so.
And is this reflected in some torsion phenomena? Homology, say?
Yeah, so yeah, the homology, exactly. So the homology has this behavior that happens when you have torsion, and it's sort of, I'd say it's reflected, yeah. In particular, the homology of this groupoid that you build here is going to be very unrelated to the K-theory of the C-star algebra.
Because here you had Z, right? And not torsion. Maybe I forget. Maybe I forgot.
So for the Grigorchuk group, everything having torsion means that this group here has a lot of torsion. This groupoid is ultimately built using this group here, and this groupoid is going to have a lot of torsion. And that will be reflected in the homology of this groupoid that we can compute.
My weak clarifies that all generators have order 2, but all group elements have order powers of 2, not necessarily.
Right, that sounds right. I wasn't sure about the group elements having order 2. But yes, but it's a 2 group, I think.
Okay.
Whatever 2 group means, I think it's one of those.
Yeah. I recall it as a finally generated 2 group, which was infinite.
Right. Yeah. So it's also right. I think it's important to note, these self-similar groups have lots of really interesting properties. Like they're interesting to group theorists. Like this is something,
Okay.
Okay, cool. So yeah, where did I get to? I started this computation. I finished the K-theory computation. And I want to point out that this Grigorchuk group is one example in a broad class of examples called multi-spinal groups that we look at. And they're all going to have the same phenomenon where you have this free product of 2 finite groups that sort of act self-similarly in a very particular way on this tree where the alphabet comes from the first group, like this. So this K-theory computation works for all of those. Another thing I want to point out is this C-star algebra here. It's a very nice C-star algebra. So in general, these C-star algebras are going to have this purely infinite flavor. Now I have to be a bit careful because these things can fail to be simple for 2 different reasons. Basically, this is a universal type C-star algebra. So there can be like if it's not nuclear, then there can be these 2, like there can be the universal and the reduced, which differ. The reduced can be a proper quotient. But one of the nice things is that we're in this setting of contracting self-similar groups. And for those, we know that we always get a nuclear C-star algebra and an amenable groupoid. So that problem we actually don't have to worry about in most of the examples we're interested in. The other thing that happens is non-Hausdorffness of the groupoid can mean that the algebra has some, let's say, badly behaved ideal structure. So the universal type algebra, or even the reduced type algebra, might have, it can have this thing called the singular ideal, which is this sort of, ideal of bad elements somehow. And this is sort of quite difficult to get our hands on. But people did actually prove that the Grigorchuk group, this ideal will, for the Grigorchuk group, in this example, this ideal will vanish. So actually, this is a simple C-star algebra. And because of that, it's actually going to be a Kirchberg algebra, a UCT Kirchberg algebra. So it's therefore classified by its K-theory. There is a unique UCT Kirchberg algebra with this K-theory. I think it's sometimes called Q2. It has a name. Anyway, yeah, so that's the C-star algebra. And so this is sort of an instance of what this is actually telling us, if we look at all of these examples, is this C-star algebra doesn't actually remember much about the initial setup, because it's very easy to build different examples here with the same K-theory and then apply this big theorem, Kirchberg-Phillips, that tells you that actually the C-star algebra is going to be isomorphic. Okay. So now homology gets more difficult, right? Because we've got a bunch of torsion. And so we have to deal with torsion in the homology groups. So again, we get this exact sequence like this. I'll just note at first that the H0 group is 0 because this will always happen. This is just to do with the size of the alphabet, really. Because the H0 group of any group is just going to be Z. All right. So now again, we understand the homology of free product groups. If we had to put the homology of the Grigorchuk group in here, we'd be lost. It would be a non-starter, right? But here we just know that for n greater than 1, the homology of a free product is the direct sum of the homologies. So we know what these group homologies are. We just get a bunch of copies of Z mod 2 like this. It's a bit ugly though, so I'll just write it as the homology of the group like this because it's sort of easier to keep track. And then what we can do is we can just see that this composition of the transfer map and the map induced in homology by this virtual endomorphism is explicitly this matrix, where again, this P matrix is induced by this 3-cycle automorphism of the Klein-4 group. So this is the analog of matrix of 1s and 0s we had for K-theory, this one over here. It's just now, right, but this gets us to this point here. So this is exactly what we've done so far. This is sort of the same argument as the K-theory argument so far, right? It's just that in the K-theory setting, we had nice free abelian groups on the left and right, and now we have F2 vector spaces on the left and the right. So we have an extension problem to deal with. Okay, but it does tell us that this homology group is finite, which is already nice, and this works for all of these multi-spinal examples I was talking about. And it turns out that because 3 is not even, we can actually determine that this short exact sequence splits, and that we again get an F2 vector space that's the direct sum of the ones on the right and left. And we can explicitly compute the dimension. I mean, okay, actually, so this dimension here, right? This is a question you could ask for someone who's just learned group homology, right? Because you have the homology of the Klein 4 group with F2 coefficients. F2 is my field of order 2, by the way. And now I'm taking the invariance of this. So I'm looking at the invariant vectors under the action of the cyclic group of order 3 coming from this 3 cycle that swaps B, C, and D. The cycles B, C, and D. So this is like, in some sense, a very elementary number. But on the other hand, it was our argument for computing this was a bit technical, but it's possible. So you compute this, and you get these numbers. So this is the homology of the Grigorchuk group groupoid, meaning this groupoid that incorporates the graph groupoid, the sort of the Kunst groupoid, the full shift on 2 generators and on 2 letters, and the Grigorchuk group itself. So we'll see that this looks very different, right, from the K-theory of the C-star algebra, which was just Z and Z. And it has this mod 3 behavior. And yeah, so at each stage, you know, this works for all of them. The first bit here works for all multi-spinal groups. This here, with this divisibility condition, this works for a class that are called Sunich groups. And yeah, and then we actually compute this explicitly for the Grigorchuk group. And if I have just a little bit of time, I want to describe why this thing splits. Like, what is 3 not being even got to do with anything? So what we have here is a nice, I think this is the right seminar for this sort of diagram. So we have a nice exact diagram. Well, it's exact except possibly for the vertical direction here. So it's exact except possibly if I include this one here. So what's happening here? Well, basically the rows are what I get from our main theorem. So this is another way of writing the co-kernel and the kernel. We actually need a version of our theorem with F2 coefficients for this. And here, this is just n-1. So the columns are coming from the universal coefficient theorem. And here, really, there should be a Tor term. But by induction, we're assuming that this Tor term is equal to all of this thing, because we're assuming that this is already an F2 vector space. And the point is that because 3 is not even, then taking the co-invariance and taking the invariance here on these F2 vector spaces, this is exact. So I don't have to, so basically it's exact when I include this 0 up here. I don't have to continue here using the first homology group of C3 with coefficients and so on. Like I don't have to continue this long exact sequence up here or this long exact sequence down there, although that doesn't actually matter. So now the point is, after a diagram chase, like the 9 lemma tells me that this thing actually is exact like this. Or maybe it's not the 9 lemma, it's something like the 9 lemma anyway. And this is exactly what we wanted to prove. We wanted to prove that this thing was a vector space so that we know the exact sequence here has to split. And that's what we wanted. Now we just, you know, we do the right summing of like the dimensions of all of these other F2 vector spaces. But yeah, I think I should stop there. And yeah, thank you for your attention.
Can you hear me? Yes. Hi.
Hello.
Oh. Can you hear me now?
Yes.
Yes, okay. And so what happened with Willie? Okay, thank you. Sorry, so is any other question? Let me check the chat. I think I can stop the recording.